Well, hello everyone, and welcome to our lesson 2 in chapter 9 of our alkynes in organic chemistry. Lesson 2, we can see that we will be focusing on section 5 through 8, the reduction of alkynes. Reduction is the opposite of oxidation. To reduce the alkynes means we'll be adding hydrogens, going from triple bonds to double bonds to even single bonds. In our 6th section, Hydrohalogenation of alkynes, adding an HX, where that X is a bromine or a chlorine. In the 7th section, we'll look at hydration of alkynes. Hydration, of course, is adding HOH. And halogenation of alkynes in the 8th section, a very brief section, adding halogens, diatomics, or even up to 4 bromines or chlorines across the triple bond. So those are the lessons that we'll focus on in the next lesson here, the video recording. And we're just bringing up to slide 16, the beginning of lesson 2 in section 5. We're going to begin with a talk of catalytic hydrogenation. This should sound very familiar from the alkene chapter in chapter 8. Just like alkenes, the double bond, alkynes undergo many of the same reactions. The first that we'll look at of these similar reactions is the catalytic hydrogenation. Taking the molecular hydrogen, H2, and sitting it on top of an arrow means we're going to add across the double bond the ene in the presence of a platinum or palladium or a nickel. All of those work well. Platinum, palladium, or a nickel catalyst is a surface catalyst, and 100% of that double bond goes to an ane, a saturated hydrocarbon. Again, this is something we just came off of from chapter 8. Over here, we now are going to compare that to an ine, which we know is the triple bond, and look, the hydrogen with the same metal catalyst, either the platinum or the palladium or the nickel, has a 100% yield of going all the way to a saturated hydrocarbon, the ane ending. In the process, we use 2 equivalents or even just excess amounts. No need to control the molarity there. The process requires at least 2 equivalents of molecular hydrogen. And we can then saturate the triple bond all the way to a single bond. Now, the first addition produces a cis alkene via syn addition. Syn means, of course, the same side, which then undergoes a second step addition to create the saturated hydrocarbon. So notice we start with the ine, a triple bond between these 2 carbons. We have 1, 2, 3, 4, 5, 6. So we are practicing naming 3-hexyne. In the intermediate stage, we have a cis-ene configuration. Notice that the carbons now in the double bond have their substituent groups coming out of the same side of the pi bond, thus the cis configuration. And then, of course, adding across the double bond again with the molecular hydrogen creates the saturated hexane. So we can think about what's happened here is we went from 3-hexyne to 3-hexene to simply hexane. So this mechanism, very similar from chapter 8, just to emphasize why it is indeed a syn addition. This metal catalyst, the palladium, the platinum or palladium or nickel, literally fixes the hydrogens onto the surface of that catalyst, and therefore the pi bond in the alkene or alkane is only able to reach down in one direction. Since the hydrogen are fixed, they're not free floating and are unable to come from the top side, so that does not happen. We can only adhere the hydrogen to the bottom side simply because the pi bond comes close enough to the surface of the metal catalyst where the hydrogens are fixed. So just reminding us of the explanation why it is syn addition only to create the intermediate, the ene. So that hydrogen is bound to the surface of the metal catalyst. This is just review from chapter 8. A syn addition occurs with an ene intermediate. Even though it's less stable than the trans, it's the mechanism itself from the catalyst that creates the cis configuration. The question you might ask is it possible to stop the reaction halfway and isolate the alkene and stop the equation from going all the way to the ane? So what we're saying is it possible to go from, in just this last slide quickly, do you think we're able to stop the equation here and prevent the saturation in that last step? So that's the question we're posing. Is it possible to convert the triple bond to a single bond and then stop? Well, the answer is yes, but we have to do so carefully. The mechanism I just showed you using the platinum or palladium nickel catalyst, those metal catalysts, is just too hard to control that last step. You cannot prevent the ene, double bond, from going to the ane. So the triple to the double to the single bond is not able to control that intermediate step that this one 100% of the time will proceed, and you'll end with the ane ending, a saturated hydrocarbon. So using the metal catalyst, it's not possible to stop the reaction at the double bond. But we can if we use a different catalyst. So that's a simplistic solution. It's still going to add the hydrogen across the double bond, but we use what is called a poisoned catalyst, one that you can stop the reaction at this cis-ene configuration and not go on to the single bond ane. So what do we look for on the arrow to know that we're going to stop halfway through? One of the catalysts used is known as Lindlar's catalyst. Lindlar's catalyst looks like this. So it's called quinoline, and it has a lot of aromatic with a nitrogen in part of that heterocycle there. Palladium, barium sulfate, and the solvent there of methanol. Lindlar's catalyst is the words. I don't really expect you to memorize the structure of Lindlar's catalyst. You'll see it on the arrow, literally is the words, Lindlar's catalyst. And I want you to just think of that as a poisoned catalyst. And all that term is kind of a harsh term to say it stops the reaction in the intermediate here at the ene phase. Now, a second choice to do the same thing is a nickel boride complex, Ni2B, if you see that on the arrow, or you see Lindlar's catalyst on the arrow, you will know to stop the equation from the ine to the cis configuration of the ene and stop. Let's try it. So this is coming from your homework. It's called a conceptual checkpoint 9.9. Draw the major products expected from each of the following reactions. So notice here we have a triple bond. This is a ine product. 1, 2, 3, 4, 5 carbons in the longest carbon chain. At position number 4, we see a methyl group. And in position number 2, we see the triple bond, so we would call that pentyne. 4-methyl 2-pentyne. Integrating some nomenclature practice. Now, notice here we see something very important. We're comparing the catalyst, Lindlar's catalyst. Think of that as a poisoned catalyst. And we compare that to just a metal, which this then is becoming surface chemistry. So remind myself to some notes over here. Lindlar's catalyst, when I see that in the presence of hydrogen, I know that the ine will convert to a cis configuration and end at the double bond. I'll call that the ene. So putting this as kind of a naming practice, we will produce 4-methyl 2-butene, I'm sorry, not but pent. And it will be in the cis configuration. if I call this pathway, pathway 1. Alrighty. So we can say that our configuration for this first product with Lindlar's catalyst is a poisoned catalyst. We need to draw 2-pentene. And so we'll have a situation that comes out in that cis configuration. 1, 2, 3, 4, 5. In position number 2 to 3 is your double bond. It is a cis configuration because both of the substituents are coming down the same side of the pi bond. At carbon number 4, you have a methyl group. So this is our answer when we have Lindlar's catalyst. Now, how about that second reaction? I'll call this reaction 2. And reaction 2, it's going to create a complete saturated carbon. And remember that this goes all the way to the ane. And just as a reminder, it does so because there's excess amounts of it. You cannot control the amount of, the hydrogen. It was just going to keep going all the way to the alkane. But to remind ourselves, there is a cis-ene intermediate, but by the time you're done adding, you will end up with 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and I drew one too many. So there is our configuration of the base, and then of course at the carbon 4 position, you have the methyl group. So we could have also drawn this starting down 1, 2, 3, 4, 5, and you could have your methyl pointing up. So either position, depending on how you started your carbon chain. So here we just went to 4. Well, now all of a sudden the names change, doesn't it? Because when naming an alkane, we have to name with the lowest number on the substituent group. So we've now produced 2-methyl, and that now becomes pentane. Good. Let's take a peek at another. This is the letter B of the same equation. So here I'm noticing the commonality is that we have hydrogen on top of the arrow. In the first series, we have nickel Ni2, boride, B. We have to recognize that as a poisoned catalyst. And the poisoned catalyst stops the reaction at a cis-ene configuration. And down below here, we have a metal catalyst, which then just creates the alkane, a saturated hydrocarbon. So let's see what we have with 1, 2, 3, 4 carbons, with that 4th carbon involved in a cyclic structure, a 5-membered ring. 1, 2, 3, 4, 5. And then of course here we'd have our carbon into a double bond. And remember, carbon number 1 and carbon number 2, we need to emphasize that this has got to be a cis configuration. And so what I really need to do is make the double bond more apparent. Let's come up, make the double bond, and then come back down for that last methyl group. That way I can clearly see that this is a cis configuration. Carbon 1, 2, 3, 4, where that 4th carbon is part of that cyclopentane, and between carbon 2 and 3 is a double bond of cis configuration. In the second, we notice that it's a simple metal catalyst, no poisoned catalyst, just the element nickel. And so now we understand that it's going to simply go to create the alkane with 4 carbons total here, counting this as the first. So we have to go 1, 2, 3, where the 4th carbon is part of the cyclic structure. Propylcyclopentane. So counting the positions helped me figure out where to put the double bond. But if we really label this, the root word comes from the longest carbon chain in the cyclic structure. I don't need a number 1 because we know that the propyl group coming off is always at the priority of number 1. So we simply call that propyl cyclopentane. Well, in our previous section, the one we just practiced, we explored those conditions of the reduction of alkyne to a cis alkene. Remember, the term reduction means adding hydrogen. The opposite is called oxidation, in which you add oxygen. So adding hydrogen is the process of reduction. And it was very specific to the cis configuration of the alkene. And just make yourself a note, it had to use a poisoned catalyst to do so, like a Lindlar's or a boron-based. And we could stop it at the cis configuration. Well, in this section, we introduce a different mechanism, a different reagent in the process called a dissolving metal reduction. And the difference here is that it will now favor the trans position for the alkene. So we have a different mechanism, a different set of reagents to use to end up with the trans configuration. Here we start with a yne configuration between carbon 2 and carbon 3. This is 2-butyne. On the arrows, you will see a sodium atom, the elemental form of sodium, and some liquid ammonia. Both are involved in a multi-step mechanism to create the trans position of the ene, 2-butene. And I'm going to show a little bit of this reaction mechanism just to kind of highlight it. And then in the next slide, we'll go through it in more detail. But to give us an idea that it's a repeating step, we have a nucleophilic attack. Notice it's the elemental sodium. Elemental sodium has just one valence electron, so it has a Lewis dot structure of Na with one electron. That electron reaches out to the pi bond, collapsing the third bond there, and it creates something called a radical anion. Now, the term radical, we need to study a little bit in chapter 10 upcoming, but it means that it has one electron instead of a set or a pair of electrons. So notice here in this first intermediate, the pi bond, which is now only a double bond, is left with just one electron. That's why it's called a radical. In the second step, we have a proton transfer utilizing the ammonia, NH3, and the pair of electrons from this pi bond reach out and put on a hydrogen. So we can see now the hydrogen has landed. And we repeat this step. The sodium elemental form with its one valence electron creates now a second dot, if you will, into that region of the lobe here. And then ammonia protonates, and we've left now with the trans ene configuration. So it's kind of a repetitive step. The sodium reaches out first, creates a radical. The ammonia then reaches out and protonates. Sodium reaches out, the radical now gets a partner, and then we add a proton with ammonia. So kind of a quick overview of that particular mechanism. I wanted to emphasize maybe with some bigger pictures step by step and just make sure we're emphasizing a few key parts to this. Notice that since the elemental form of sodium has just one electron, when we transfer it, we use a fish hook arrow. So that means that I just reach out with one side of an arrow, not two. And notice it's the same here. These are fish hook arrows showing the single electron movement. So in that very first step, we produce a radical cation intermediate. The term radical means there's one electron not partnered, but just alone in this lobe, this p lobe of an electron orbital. And it's a negatively charged region up here, but it's a radical region down here because it's simply that one electron. So I wanted to make note that you're seeing for the first time really these fishhook arrows instead of a double-headed arrow. When I move a pair of electrons, we use a normal head on the arrow. And that's what happens in step 2 and 3 when we protonate. So notice here, whoops, that jumped. The second step of the mechanism has the pair of electrons in this p orbital reaching out to the ammonia's hydrogen, collapsing the bond. And of course, this would form the amide nucleophile. And then once it's protonated, you see that hydrogen now adding. Notice that it's a double-headed arrow in this step because pairs of electrons are being moved. So the double-headed arrow right here. But in that next nucleophilic attack, again, since sodium has just one electron, we use the fishhook arrow, just a one-sided arrowhead, because I'm moving a single electron instead of a pair of electrons. And then, of course, in the last step, you protonate. Whoops, that jumped. I apologize. You protonate with the ammonia, and you create a transene. So when we start seeding for next chapter, chapter 10, and do radical chemistry, we're going to be doing a lot of those type of arrows, moving just a single electron. So putting it all together, the outcome, this is the important part, understanding radical chemistry is part of the mechanism. Put it all together for this outcome. We started with an yne, a triple bond, 1, 2, 3, 4, 5, 6. So this is 3-hexyne. And here now we went to a trans configuration where we have at position 3, we now have a double bond. So we hear it as 3-hexene, and we can see the trans configuration because on the pi bond, the priorities are coming on opposite sides of the pi bond. So that's the trans configuration. A little bit different mechanism. I wanted to stress that step by step. And we can put it into use with some practice problems coming from your conceptual checkpoint 9.10. When we treat the following alkynes with sodium, sitting on top of the arrow is sodium, and liquid ammonia, you'll see that on the bottom of the arrow, predict the major product that's expected. And I just want us to emphasize when you see sodium and you see the liquid ammonia, you just in your head say, that goes to a trans configuration of the double bond ene. 1, 2, 3, 4, 5, 6. This is called 2-hexyne. We need to convert that into trans 2-hexene. So helping with the nomenclature, we can kind of figure out what our product then needs to be drawn as. I need 6 carbons, 1, 2, 3, 4, 5, 6. I'll just number in the same direction. There we go. And between carbons 2 and 3, we'll have a double bond. And I just want to remind you when we have a trans configuration, on the opposite sides of the pi bond, we see that the groups are coming out. So that's a trans configuration. From carbon 2, the priority group is pointing up, and in carbon 3, the priority group is pointing down, a trans configuration. Here again, we see that on the arrow, we have sodium in the presence of liquid ammonia. Here we have a cyclobutyl. Cyclobutyl comes to a 4-cyclic ring. And from here, we know to create the trans configuration. So my 4-carbon ring lead down to a double bond, and out from the double bond will be the second cyclobutyl group, and we have a trans configuration. Easy enough. Good work, team. And let's kind of just reflect on all the things we've just learned. The first, so far, hydrogenation. We understand that hydrogenation simply means adding across a pi bond. We're going to add more hydrogen. If we add hydrogen to an yne, the triple bond, in the presence of this poisoned catalyst known as Lindlar's catalyst, or you could use a nickel boride catalyst, it's the same effect, you end with your cis-ene configuration. End of story, it stops. That's your product. In a next treatment, if you added hydrogen across the metal platinum, it will go on and create the ane ending. This is not controlled well, so that just simply means any type of pi bond in the presence of hydrogen with a metal catalyst just goes straight to makes the ane. There is no intermediate. I cannot stop it. The triple bond all the way to single bonds. And then the last one we just practiced, working with sodium and liquid ammonia, ended with the trans configuration of the ene and stop. But if I wanted then to continue to create the ane as in any condition, hydrogen and the metal catalyst will saturate the bonds. So with that in mind, you're just asked to practice some reagent choices. This is checkpoint 9.11. It says we need to identify what type of reagents we should use to achieve the following transformations. So just to remind yourself, when asked to pick from the reagents, this was the slide we just used. Do we want to use hydrogen in the presence of Lindlar's catalyst? Do we want to use hydrogen in the presence of platinum? Or do we want to use sodium in liquid ammonia to create the trans-ene? So with the poison catalyst of Lindlar's, we get a cis. With the sodium workup in ammonia, we get a trans. And anytime we just want to get rid of any type of pi bond, hydrogenation in the metal catalyst will do it for us. So those are the choices as we kind of tackle this. Here we have a triple bond, 1, 2, 3, 4, 5, 6 carbons long. 2,5-dimethyl-3-hexyne. I notice that I'm creating a cis configuration. In the 6 configuration, we've now moved it to cis. Well, we'd have 2,5-dimethyl, 3-hexene. Let's write that just for the practice. Here we have 2,5-dimethyl hexyne. And up here we can see this now as in a cis configuration, 2,5-dimethyl. And at carbon number 3, oh, I forgot that in here. I'm sorry, I have to erase because I made a mistake. I need to let you know where that triple bond is. 3-hexyne. Thank you for telling me. I heard you through the video. And that comes here again, 3-hexene. And now what gives us that cis configuration? And I know that you've got there already. You went and said, well, that's hydrogen and Lindlar's catalyst. So those are the choices I would place on the arrow to create this particular product. So the Lindlar's catalyst in the presence of hydrogen. Down here, I can see that we have, again, looking through at a trans configuration of 2,5-dimethyl-3-hexene. And this time, if I want it to be trans for that particular configuration, we need to pick a different tool. And I'm just trying to pull that slide down. And we could see that that trans came from the sodium workup, sodium and liquid ammonia. And so that's what I'll be placing on this arrow. The mechanism, of course, would be involved in a radical. But in the first, we produced cis, so the catalyst is Lindlar's. In the second, we produced a trans configuration. So the catalyst is sodium, elemental sodium, in the presence of liquid ammonia. Same idea. Here's another chance to practice. I have an ene between carbon 2 and 3. 1, 2, 3, 4, 5. So this is 2-pentyne. And I've gone to create 1, 2, 3, 4, 5. This is a trans position. Oh, my pen is kind of falling behind the recording. Trans for trans. And in the trans position, we know that the choice of product here is the same as we just picked, the sodium and the elemental ammonia. This happens when I record because there's a lot going on my screen. Down here, oh my gosh, this is all saturated. So we wanted to pick a trans configuration here. Here we want to go all the way to the ane ending. So that's the job of just molecular hydrogen in the presence of a metal catalyst, such as platinum. Great work. Let's learn something new. Hydrohalogenation of alkynes. Hydro, adding an H. Halogenation, adding an X, where X is a bromine or a chlorine. In our last chapter, chapter 8, we focused on the alkyne chemistry, adding across the double bond, where we followed Markovnikov's rule, where the hydrogen adds first to create a carbocation intermediate. The carbocation is the one with the most substituents to create stability. And in the next step, the halogen adds on to the most substituted carbon. So we ended up with 1, 2, 3, 4, 5, 6. At position 2, we'd have a halogen in a 6-carbon chain. Now in this particular reaction, still the same, we have a terminal alkyne. In the terminal alkyne, adding a single equivalence of HX across the triple bond, still follows Markovnikov's rule, where we end up with an ene, because there's just one equivalent so far, and we'll still follow by putting the halogen on the most substituted carbon. If we have excess amounts of the hydrohalogen, excess just simply meaning enough to at least have a second equivalent, perhaps more. Notice here then across the double bond, we place both halogens in the most substituted carbon. This was a term we learned last chapter called a geminal dihalide. Geminal means the halogen is on the same carbon. So the kinetics, it really gives us an idea of the mechanism for this reaction, and it's very unusual. Probably one of the fewer times I've ever heard of a termolecular kinetics. So termolecular means there must be 3 molecules involved in the collision. And I know that that's extremely difficult to get to work, but this is the mechanism that's proposed to help explain the outcome that we see. So what it's saying is that the alkyne is first order. So we see first order with respect to the alkyne, meaning that it's one molecule of the substrate. But it is second order with respect to the hydrohalogen, meaning that it's going to require 2 molecules to get us all the way to the ane ending, a termolecular process. So here's the proposition, the proposed mechanism. Notice that we're seeing a transition state. So that means that it's like a concerted one-step mechanism where one unit of our hydrohalogen, this bond, this single bond is reaching to the first carbon in the triple bond. At the same time, the pi bond is going to abstract the proton from the second group of the hydrohalogen. But I have two groups, second order with respect to HX, in one substrate. So it's first order with respect to the substrate. They're the yne, the triple bond molecule. We go through a transition state where the H and the X add across the double bond in that transition state. And they're just a proposed mechanism, but there's probably, as the text was telling us, there's more likely competing mechanisms that are occurring. In the second step, we end up with the geminal dihalide, probably through a molecular equation. So just overall, sorry, that keeps skipping. Overall, we have a geminal halide, and it follows Markovnikov's rule, in which the halogen adds to the most substituted carbon, which of course is the carbon interior in this terminal alkyne. Notice what I'm saying there in terms of terminal alkyne. That tells me that the triple bond is at the end of the carbon chain between carbon 1 and 2. That's a terminal alkyne. And so when I'm looking at Markovnikov's rule, at carbon number 2 interior, the second carbon is the site for attachment of those halogens. Let's take a practice. This is very simple. Again, went through a mechanism of a molecular in terms of kinetics, but we're asked to predict here. So a simple prediction: study what's on the arrow. Excess amounts of HCl, a hydrogen and a halogen. In terms of the mechanism, we follow Markovnikov's rule that tells us we have 1, 2, 3 carbons across here. Here's 1, 2, 3 carbons. And at carbon number 2, which is the second carbon here, is the most substituted carbon. So not at the terminal end, but the second carbon adds to the, that's the position where we're going to add our chlorines to create a dichloro product, a geminal dichloro product. And that's it. Excess amounts of HCl follows Markovnikov's rule, putting the double chlorine onto the same carbon in the carbon that is most substituted. There was an exception in Chapter 8, very specific to peroxides and HBr for our alkene chemistry. And it comes up again in Chapter 9 with our alkyne chemistry. In the presence of peroxides, HBr specific, it only works for HBr, not any other halogen. We add that halogen as an anti-Markovnikov addition in the presence of peroxide. So now notice, this is just review from last chapter. Between carbon 1 and 2, Markovnikov would put the halogen on the most substituted. That's not what we see. What we see is the least substituted at the end of the carbon chain, anti-Markovnikov. So onto the less substituted carbon, we place the halogen. So a very similar reaction when we see HBr in the presence of a peroxide, and we start with a terminal alkyne, position 1 and position 2 of the triple bond. What happens is that we end up creating a mixture of E and Z isomers, a mixture of the addition to an ene and stops. So a triple turns to a double with equal amounts of the trans. Trans means the bromine is coming up while the carbon chain is coming down. that is the opposite sides. Opposite starts with a vowel, so I know that that's the E conformation as well. And this is the cis conformation, where the double bond has them coming out of the same side. The same side is also called the Z conformation. So adding a peroxide into the mix of HBr makes it form an anti-Markovnikov with a cis-trans isomer coming out. And thinking that through, this is what we've learned so far. I want us to connect something from the first lesson to something from this lesson as well. We have taken a terminal alkyne. Notice that the carbon is at the end of the chain, a terminal alkyne. And we can add excess amounts of HX. HX is either HBr or it's HCl specifically. And we get a geminal dihalide following Markovnikov's rule. And I bring this out because in the last lesson, we practiced this very reverse reaction where it says, let's see how we can make a terminal alkyne. And we started with the geminal dihalide, and we added excess amounts of sodium nitride in the presence of ammonia, followed by a water workup to go back and protonate. I made myself a note here to force you to remind yourself from lesson 1. Back in slide 15, we did a mechanism. That's a busy slide, but we did a mechanism that says if I have a dihalide in the geminal position, just as I'm showing here, we talked about how, how at first this strong nucleophile of ammonia reaches out for the beta proton. And when that collapses then, the beta proton up here in this methyl group, we created an ene intermediate. And the next step, the amide pricked off another proton, collapsed that bond, and then we ended with an ene going to an yne, sp hybridization. And recall from our previous lesson that amide is so strong, so hard to control, that this proton, the terminal proton of a triple bond, is very acidic. So the amide then also plucked off that proton. That's the reason that we added the water molecule. The water molecule was used to reprotonate the alkyne. So when I say go back and look at that lesson as review, that's specifically why. Here's the slide that we just were viewing. We spent time just now going from the terminal alkyne to the geminal dihalide through excess amounts of a hydrohalogen. But recall, in the last lesson, we spent a great deal of time with the mechanism going the exact opposite way. So we have hydrohalogenations as the addition, and then looking at the elimination process to create the terminal alkyne. Good review at this time. So let's put it into some practice with 913, a conceptual checkpoint. What's happening in this picture? So what we're seeing here, starting material, let's kind of get an idea. We have a geminal dihalide, and it's a chlorine group. Alrighty. And we're going to treat that with, and I look at these two steps really as part 1, part 2. That tells us that the geminal dihalide is going to turn into a terminal alkyne. I just said the geminal dihalide is going to go back to form the terminal alkyne, and the water is used to just simply protonate back the triple bond. So with the first workup, here's what I have so far. And I have an aromatic ring, 2 carbons that have now converted into a triple bond from step 1, step 2. That's where I'm at so far. There is a next step, and it's really step 3, but I call this the first step simply because those two are used to create the triple bond. So I don't need to show the intermediates or anything. I'm just saying that produced, I'll call that step 1, the first arrow. And now the last step here with that workup of HBr and ROOR. So on this arrow, let's place the last step. And notice this is a peroxide. You have hydrogen bromide in the presence of a peroxide. So I want you to think Anti-Markovnikov. In the anti position, that means that the bromine is going to add to the least substituted hydrocarbon. And that at the terminal end, so we have an ene that forms, that double bond. The bromine can either be in a trans position, and the bromine could also be placed in the cis position, coming out on the same side as the phenyl group there. That's Br. There we go. So you'll have a mixture of configurations, the trans and the cis. So step 1 really was workup 1 and 2 together to create the terminal alkyne. The terminal alkyne then is treated with a peroxide workup of HBr, anti-Markovnikov, to produce the cis and trans at carbon position 1 of this particular cyclic aromatic ring. I'll ask you to just try one and see what you think. I mean, anytime, remember, pause the video to digest, come back. Do this in short amounts, pause it, come back, and then pick up when ready again. Don't try to sit here all at once. I know it's a long lecture. That's the beauty of a video lesson. Pause and come back. Let's take a peek at this reaction and try to figure out how we could achieve it. What are some reagents that would achieve the following transformation? Well, let's kind of figure out what we have and what we want to achieve. I notice that the starting material is still a geminal dichloride. It's a geminal dihalide, geminal dichloride, and it's at the primary position. This is also a geminal dihalide, but now it's moved from position 1 to position 2. Well, I don't know of any single reagent we've learned so far that just picks up a couple of chlorines and moves them down the carbon chain. So we got to think about getting it there. One thing I want to do is, first of all, let's get rid of the chlorines. And what I want to do is to create a terminal alkyne. So the goal is to create the terminal alkyne so that I can then add across a second chlorine group and get it to add Markovnikov in terms of additional reaction. So make a terminal alkyne. Get rid of the chlorines so we can place them on again later. So with this, to create a geminal dihalide, we're going to use our excess sodium amide in the presence of ammonia. And then we'll work it up with a second step. We have to add the water to protonate back the terminal alkyne. So this NaNH2, that didn't come out well, NaNH2 sodium amide in the presence of ammonia creates a terminal alkyne with a negative charge, and then we protonate back that last carbon with the water workup. So here we'll have our 5 carbon, where carbon number 1 to 2 is a triple bond. 1, 2, 3, 4, 5. Nope, that's not right because it comes out at 180. 1, 2, 3, 4, 5. Triple bond. Notice I needed to make sure carbon number 3 was still linear. So here's 1, 2, 3, 4, 5. That's a 180-degree bond angle. That's where we're at so far. We created a terminal alkyne using sodium amide with ammonia, followed by a water workup to protonate the end. Now I want to add a chlorine group back, but I want to do so in the Markovnikov position at carbon number 2. And that's as easy as saying, let's just take excess amounts of HCl. Excess amounts, not just one unit, but lots of it to create dichlorine products. So here we end up with 1, 2, 3, 4, 5. At position number 2, we're adding 2 chlorines and have created a geminal dichloride at carbon number 2. So what's cool about this reaction is that it really looks like you just picked up and moved the chlorines from carbon 1 to 2, but the secret there is in doing so, step 1, we had to get rid of the chlorines first and create a terminal alkyne, and then we put them back on following Markovnikov's rule, and that puts it back onto position 2. Nine 7, we're in the home stretch. Hydration of alkynes. You think of hydration as HOH, adding across hydrogen and hydroxyl group across the double bond in last chapter, and a triple bond in this chapter. This was one of the very first reactions we actually spent time with in chapter 8 together, taking a double bond in an acid catalyzed reaction. The acid catalyzed reaction allows for carbocation intermediates for that alkene, but it did follow Markovnikov's rule. Now, this went very well for an alkene, but alkynes are a little bit sluggish at this, so we have to catalyze them to force that issue to occur at a meaningful rate. So with the catalyst, we have to put it in the presence of mercuric sulfate. I would call that mercury 2 sulfate, HgSO4. And that's just really compensating for the sluggish rate of the reaction without the catalyst. This reaction is different in the sense of the outcome, very different for the outcome from last chapter ene to this chapter ine. The outcome of the hydration forms an ene-ol intermediate. Ene means double bond. And the ol is from the alcohol OH functional group. We have a double bond, ene, and the functional group ol. That's the ene-ol intermediate that forms in this mechanism. Let's break it apart slower. The alkyne attacks the mercury cation. Now remember I said in the presence of a mercury catalyst, HgSO4, but the mercury ion, which is +2 charge, and the sulfate truly is a spectator. So notice the sulfate isn't even written about, but it just needed a last name. The mercury +2 ion is involved in this first step. It's a positively charged ion, and it has a lone pair of electrons. The pi bond from the triple bond ine reaches out and attaches to the mercury ion and creates this intermediate, mercurium ion intermediate, has mercury on it. In our next step, the water then reaches out and attaches to that positive carbocation region. We called this a protonated alcohol. And again, the second water molecule just reaches out to pluck off a proton, deprotonates that alcohol, and it created then the alcohol group. Notice that the mercury ion was there the whole time to prevent any type of rearrangements from occurring. Very similar to using mercury from the previous chapter to hold a position and prevent any type of rearrangement. Same strategy here. As we go on, the second pi bond now needs to be eliminated. So as we think about what's happening here, that pi bond reaches out for an acid catalyzed reaction. Proton reaches out, and we form an equilibrium between two products here. The transition between the single bond hydroxyl group and a double bond hydroxyl group, back and forth, and finally then it equates at the ene-ol position. So let's define ene-ol. Notice that it has like you see that it has two positions here. So we'll follow that up in a moment, but the ene part here is the double bond, and the ol part here is the hydroxyl group. Ene, ol, intermediate. Now, all of that mechanism is just allowing us to see what's happening in terms of the process. I'm not going to ask you to draw that mechanism at this point, but we'll work to it. The enol that's formed here is still an intermediate, and it tautomerizes to a ketone. It's called keto, enol, tautomerism. I know it sounds like a foreign language. Keto, enol, tautomerism. Speak English, Hansen, right? Well, all that simply means is there is an equilibrium between the enol and the ketone that's the more stable configuration between those atoms. And I wanted to do some definitions for you. The term enol and ketone are tautomers of one another, and that might be a brand new word for us. And so I took the time to just write out what that definition means, a tautomer. It says each of two or more isomers which exist together in equilibrium and are readily interchanged by the migration of an atom or a group of atoms within a molecule. Let's put a visual to that. Notice the hydrogen, when it's on the alcohol, places the double bond in the enol position. If the hydrogen migrates to the end of the carbon chain and we place the pi bond up to the oxygen, we have a functional group now called a ketone. And thermodynamics favors the ketone over the enol position. So all of this, my friends, all of this is just kind of coming out to let us know that a keto-enol tautomerism is just a process where these two competing positions, the enol and the ketone, are in equilibrium, and yet one side is actually favored over the other. Let's put it to use. Let's process. Here is an enol. These enols cannot be isolated because they just rapidly tautomerize to produce ketones. In each case, and this has, letters involved, I've picked letter A, draw the expected ketone and show a mechanism for its formation under acid-catalyzed conditions. So here we have an acid-catalyzed, and that's kind of critical because that's really the first step in our mechanism. So in our first step, the acid, I'm going to just draw that out as the hydronium ion, H3O plus, and that plus sign is actually on the oxygen, so it has a formal charge there of +1. The pi bond of the enol is going to reach out and pluck off one of these hydrogens. So the first arrow originates at the pi bond, and it's going to connect to one of the 3 protons in the hydronium ion. That forces this bond to collapse. And what else results then? Well, we begin with this equilibrium, this process in which we have 2 competing structures form, dynamic equilibrium. And in the first structure, we have 1, 2, whoops. All I want to do is count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. At position carbon 2 to 3. So I have 1, 2, 3, 4, 5. The hydrogen that is now attached to the hydrogen, and I have the positive carbocation in this position. In dynamic equilibrium there, we also have the double bond O leading to the H and no positive charge on that particular carbon. So with the process of these two competing structures, let's pick up the arrows then. What happens here is that this particular arrow, I should probably add the oxygen dots. We know that they're there, but I just didn't put them. So we have two sets of dots on this first oxygen. And what we have here now is not a dot. We have this positive oxygen because that's where the positive charge migrated. In the first structure, the positive charge is on the carbon, and on the second structure, the positive charge is on the oxygen. So there's no dots there. All right, so that was kind of critical just to kind of help us make sure we see the octet rule and what's got a formal charge. So with the next step to go between these two, what we see happening is a set of electrons being moved down to this bond. That's where the next bond here is created. And to create the second structure from the first, we'd collapse this bond and make the set of dots. So we're just kind of showing how these two structures go from one to another. We have a next step occurring, and that's the water molecule now. And in this water molecule, that electron-rich area of the oxygen is going to come up and pluck off this hydrogen. And when it does so, you can see that the ketone is finally created. 1, 2, 3, 4, 5, with a ketone product. When an enol is in dynamic equilibrium with the ketone, we call it tautomerism. The tautomerism is the shifting of electrons and atoms to create isomers of one another, tautomers. Let's remind ourselves of the words, tautomer. What we were just being asked to do is to create that dynamic equilibrium of this tautomer. Tautomer says they're isomers that exist together in equilibrium and are readily interchanged by migrating an atom, in this case the atom is a hydrogen, and the electrons of a pi bond. What we just drew, the answer to the question that we just worked through together, was this particular series of equations. We started with an enol. The pi bond reaches out for the proton on the acid catalyst. When it does so, we have a resonance stabilized intermediate. Notice that these two structures are interchangeable based on the arrows that are being shown. So from this structure, I can shift a pair of electrons down, and when doing so, I create the double bond. The formal charge then moves from the carbocation up to the oxygen. Go from this structure back. Well, we can see that this bond collapses. When this proton is being abstracted, this bond collapses, and then we can have the ketone produced along with regenerating the hydronium catalyst. So that also regenerated. As I pluck this off, the catalyst gets regenerated. That's what we very carefully drew in our first practice in Skill Builder 9.16. So 9.16 has many letters with it, B, C, D, and we just want to make sure you see where you're going to find the mechanism. In another checkpoint, 9.18, here's an opportunity to kind of think about what would happen if I start with this terminal alkyne, 1, 2, 3, 4, 5, 6. At carbon number 6, we have a cyclopentane. So a terminal alkyne, and we're going to treat it in the presence of an acid and mercuric sulfate. So with this particular question, we're given on the arrow an acid catalyst. You might see that written as either like H2SO4 or H3O+, or aqueous. You might see water with a proton. Many different ways to denote an acid. And then the mercuric sulfate. So thinking about what happens in the first mechanism is that we create the ene-ol product. But I'm going to put it in brackets because it's very difficult, if not impossible, to isolate the ene-ol before it converts to the ketone at the end. So I'm going to put it in a bracket to let you know it's produced, but impossible to isolate. And then what we have here is going down, up, down, up. There's carbon 2, carbon 1, and we're at this double bond. And coming off then, I'll make the double bond go down. And that way I can point up to the OH. We have the ene-ol. Here's carbon 1, 2, 3, 4, 5. And at carbon 6, we have the carbon that's part of that cyclopentane ring. So between carbon 1 and 2 is now the double bond. That's the ene. And at carbon 2, we have the ol. And I put it in a bracket to emphasize you cannot isolate and call that your final product, because it will rearrange through a Tautomerism and go on to form the ketone. Cyclopentane, 1, 2, 3, 4, 5. Whoops, I missed one. That's why it's always good to number, make sure you're not missing any. Come down, up, down again. And at carbon number 2 is the ketone. Let's count to be sure I have enough carbons. I'm just thinking, sorry for the quiet, I'm just thinking I have carbon position 1. At carbon number 2 will be the ketone, carbon 3, 4, 5, and at the 6 we finally meet up with the cyclopentane. There I have it. So at position 2, the alcohol first with the ene between carbon 1 and 2. Going on, the ketone is formed at carbon number 2. So when we treat with these aqueous acid in the presence of mercuric sulfate, that terminal alkyne undergoes a Markovnikov addition of HOH, and that alkyne is going to produce the ene-ol. The ene-ol is not isolated, and it goes on to form, at position 2, the ketone. What might be an alkyne we could start with to prepare each of the following ketones via acid catalyzed hydration? So I look at this as saying, you know what, we're working backwards. So working backwards is an opportunity to kind of do a retrosynthesis. And that word means tell me what you're going to start with, right? And all we really need to think about is what would the alkyne need to look like? And I understand then the alkyne has to be between the 2 carbons at the end. I need a terminal alkyne to go on to produce the ketone. So this question becomes quite simple, and just 1, 2, 3, 4, 5. We need the alkyne to be at position 1 to 2, 1 to 2, and then coming straight out is 3, 4, 5. This is the triple bond. I then emphasize that it comes out to keep that straight 180-degree bond angle. 1, 2, 3, 4, 5. And at position 4, I still need that methyl group. That's the alkyne I would use to produce the following ketone. It's as simple as that. Find the position where the double bond O, the carbonyl carbon, That's the C double bond O functional group. And it's at carbon 2, so that tells me the terminal alkyne is just going to replace the ketone with a triple bond at the end of the structure. That one was pretty easy. I like to work practice problems, so pause anytime you're ready, come back, take breaks if you need them. We have a last little topic here, hydroboration-oxidation of alkynes. I'm trying to bring back as much review from chapter 8 as possible. Hydroboration of alkynes is very similar for alkenes. This is something I went back to my chapter 8 slides and found. This is taking an alkene in the treatment of boron trihydride in THF with a peroxide workup, and we get an Anti-Markovnikov addition. So it's very regioselective, and it also produces an enol that tautomerizes actually to an aldehyde instead of the ketone. So interesting here. Here is a terminal alkyne, and a moment ago, the double bond ended at carbon 2, the most substituted carbon. It followed Markovnikov's addition. But now in the treatment with boron and peroxide, we really have the same ene-ol intermediate, but the OH is added to the carbon of the least substitution. So it's not following Markovnikov's rule, and that means the double bond carbonyl carbon goes to the least substituted carbon, and that produces an aldehyde since it's at the end of the carbon chain. If I had produced a ketone, it would be interior in the carbon chain, but since it's at the end position, we call it an aldehyde. And this occurs through the same type of tautomerization, but it's base catalyzed. So with this particular structure, it tautomerizes between the enol and the alcohol and over here, and then finally the aldehyde that's produced. So thinking through about anti-Markovnikov in the presence of boron. Proton transfers occur, the enolate ion is formed, very similar mechanism, just located at the end of the carbon chain instead of interior to the carbon chain. So look for some of these reagents on the arrow. If I see a terminal alkyne, and I see any type of boron in the presence of peroxide, those are key to know it's anti-Markovnikov, and it will go on to produce the aldehyde, just meaning that the carbonyl carbon is going to be placed at the end of the terminal chain instead of interior where the ketone would be drawn. So let's take a peek at this one. Here is a problem where I see the reagents 9-BBN. B stands for boron. I mentioned that boron often exists as a dimer, one connected to another. And I noticed that there is peroxide on the arrow as well. Those are my two keys that my head has to say Anti-Markovnikov. So I have a cyclic structure, 6-membered ring. Coming down, I have 1, 2, 3 carbons. 1, 2, 3 carbons. And at the very end of that carbon chain, you'll end up seeing that you have the aldehyde formation. Now, if it asked for the enol intermediate, I could take you there. Let's come down and go the intermediate. And I'm going to put that in a bracket and then show you that it can work up to the aldehyde. This question didn't really ask for that. It just said, what's the major product? So that's why I just drew the aldehyde straight out. I had 1, 2, 3 carbons coming out of a cyclohexane. 1, 2, 3 carbons coming out of a cyclohexane. At the very end carbon is going to have a carbonyl group, the aldehyde functional group. But if it asks you to draw the enol intermediate. Let me just model that for you as well. I have one, whoops, I should come down first just to make sure I'm doing the same stereochemistry. Come down, up, down, and here's your OH, and there's the ene part. Between carbon 1 and 2 is a double bond. The anti-group of the OH addition, this would be your ene-ol intermediate. Notice that the question didn't ask for that, but I wanted to emphasize if you're asked for the enol intermediate, I wanted to present it to you. And let's peek at one more question here, just another opportunity to practice, encouraging you to take breaks as you need them and come back and just work with me. We're going to identify the alkyne that I would use to prepare each of the following compounds via hydroboration-oxidation. So this is coming from yet another homework question. It's number 21 for your homework, 9.21. I just selected letter A. And I wanted us to notice that this is an aldehyde. And that leads me to remember the Anti-Markovnikov. Boron with peroxide needs to be on the arrow somewhere, right? But as I'm just asking you, what would the original alkyne need to look like? So I have 1, 2, 3, 4, 5, 6 carbons in this carbon chain. And between carbon 1 and 2 is going to be a triple bond. So I'm going to draw, here's carbon 1 to carbon 2. Coming straight out of carbon 2 is carbon 3. So I have a triple bond between carbon 1, 2, and there's carbon 3, keeping my bond angles together. And then I can start branching 4, 5, 6. On carbon number 5 is a methyl group. So here is the terminal alkyne that produces the aldehyde. And sitting on the arrow, of course, is the hydroboration-oxidation workup. Just to put it on one slide and reflect a moment, we have a terminal alkyne. In the presence of an acid catalyst and a mercuric sulfate, we produce Markovnikov addition ketone. In the presence of a boron compound with the highly oxidative peroxide, boron oxidation occurs. That's a P, peroxide. We get an aldehyde, which is anti-Markovnikov. I wanted you to spend time with this particular learn the skill just to kind of achieve some transformations. We're just asked to identify the reagents that you'd use to achieve the following transformations. And all it's giving you is really an opportunity to practice recognizing the terminal aldehyde that goes to a ketone. I know that we will use acid catalyzed hydration in the presence of mercuric sulfate or mercury 2 sulfate. If it were an aldehyde and you saw an anti-Markovnikov addition, an aldehyde means that the carbonyl, the double bond O, ended at the least substituted terminal carbon. You're going to use a boron workup, a boron oxidative process. And you can practice those with problem 9.22. 9.22 gives you just a little bit practice of turning in reagents into one or the other. But all it is, my friends, is recognizing if it produces an aldehyde or a ketone. The terminal alkyne produced an aldehyde. And what I mean by that is the carbonyl is on the very first carbon. Therefore, we know it's an anti-Markovnikov addition. You're going to use some sort of boron reagent in the presence of sodium hydroxide, or I can put H2O2 to recognize peroxide. You might see that as HOOH. You might see that as ROOR. All of those are letting you know that it's a peroxide reagent. You might also see boron written, as we just saw a moment ago, as 9BBN. There's lots of different ways, but the key is to notice that it has a boron component and a peroxide component, and you'll end at the aldehyde position. And if it's a ketone position, you know that it's going to be an acid catalyzed workup in the presence of mercuric sulfate. So given these two choices, is it a ketone or aldehyde, lets you figure out which reagent to then use. And I am pleased to say that this is the last slide for lesson 2 and by far the easiest section in our chapter. And I like to end it with one slide for an easy section. It's called the halogenation of alkynes. The halogenation of alkynes means I'm going to take either diatomic chlorine or diatomic bromine and fill the pi bonds until I saturate the compound. I have a triple bond. Those are just in terms of sp hybridization, and bring it all the way to sp3 hybridization by adding as many halogens as you want across the double bond. And it does so in a way that is controllable. Let's say I add just one equivalent. One equivalent is going to create a trans conformation over the cis, just based on stability. The trans gives the halogens more room, where this has a little bit of steric hindrance. So the major product is the more stable conformation. And just realize that if I did yet a second treatment, one more treatment of, let's call this X2 again. I was going to write bromine, but we can just keep it general. Add another one of these, and you're just going to get all saturation. So instead of this configuration of sp2, we'll just make it 1, 2, 3, 4. This could be your R, this could be your R, but you end up with X's all created across the bonds. And that really is the last. There's no practice with that. It's just saying, depending upon the number of equivalents, you're going to add your halogens. You may stop it at the ene phase by controlling just the amount with one equivalent. You'll end up with the trans halogen. If you add a second equivalent, you're going to add across that double bond and have 4 halogens come out. I'm so super proud of you for making it through lesson 2. I look forward to receiving your notes. Have a good day.